Hello, let me present you solutions to selected homework problems part 2. And the first problem I'm going to consider is the following one. Is the set of rational numbers open or closed? So actually I'm going to prove that the set of rational numbers is neither open nor closed. And that proof is based on the following fact. So I'm going to recall you that the set Q of rational numbers and the set I of irrational numbers, that is defined as the complement of Q, are both dense in R. Okay, so let's first prove that Q is not open set. Okay, so again, recall you that A is an open set. Okay, if for every element of A we can find delta greater than 0, so that the interval x minus delta, x plus delta is contained in A. Okay, so let's take an element Q, an irrational number, arbitrarily, and let's take arbitrarily delta greater than 0. Okay. Okay, so if now we consider two numbers, Q minus delta, that's denoted by A, and number B, Q plus delta. Okay, both of these numbers are real. Okay, and then since I is dense in R, we can find irrational number R. Okay, so that A is less than R, less than B. Okay, so that means that this intersection of this interval Q minus delta, Q plus delta with I is not empty. Therefore, this interval is not contained in Q. And it's true for every Q from the set of rational numbers and for every delta greater than 0. Okay, so therefore Q is not open. And moreover, we can say that interior of Q is empty. So neither point of Q is actually an interior point. Okay, so now analogously we can prove that I, the set of irrational numbers, is not open. Okay, again, since it's not open, Q, which is defined as a complement of I, is not closed. Okay, why? Because again, we have that a set A is closed if and only if its complement AC is open. Okay, since I is not open, the proof is very similar to this one, again because Q is dense in R. So the interior of I is also an empty set. Q cannot be closed. Okay, so therefore the set of rational numbers is neither open nor closed. Alright, in the next problem I'm going to prove that set E is dense in R if and only if the interior of its complement is empty. Okay, so again, let me recall you two definitions. So recall that E is dense in R if and only if for every 2 points A and B from R, say A less than B, we can find a point R from E so that A is less than R, less than B. Okay, so let's prove the first part. Okay, so suppose that set E is dense in R. Okay, and let's show that in this case that its complement has no interior points. Okay, so again, take arbitrarily a point X from the complement of E, R minus E, and let's consider any given delta. So since E is dense in R, we can find some number R from E so that X minus delta less than R less than X plus delta. So in other words, for every x from r minus e and for every delta, this interval x minus delta, x plus delta, intersection e is not empty. Okay, so therefore that interval cannot be a subset of r minus e. So this interval is not contained in r minus e. And again, since it's true for every x, for every delta, that set r minus e doesn't have interior points. Okay, so now let's prove the second part. So now let's suppose that the set of interior points is empty, and then let's prove that in this case E is dense in R. So in other words, we need to show, again based on definition, that for every 2 points A and B, we can find the point R from E that lies in between A and B. Okay, so let's suppose it's not so. Suppose that we cannot find the point R from E that lies in between 2 points A and B. Okay, so in other words, this interval AB doesn't contain any points from E. Okay, so therefore this interval is contained in the complement of E. So therefore, if we have an interval that's contained entirely in that set, therefore the interior of this interval of the set is not empty. Okay, so that actually is contradiction. Okay, because we have that the interior of the set is empty. The last problem for today's video presentation is the following. Let's define a new set function m double star as follows. So we consider all open sets that include A as a subset, and then we consider infimum of their outer measures. So let's show that actually this new set function m double star is nothing more but the outer measure m star. Okay, so let me denote, say I denote by B this set formed by outer measures of every open set O that includes A. Okay, and then in this case m double star of A is defined as infimum of this set B. Okay, so first we know that from monotonicity, so m star is monotonic, we know that if A is a subset of O, then the outer measure of A doesn't exceed the outer measure of O. Okay, so in other words, the outer measure of A is the lower bound for this set B, because it's true for every set O that contains A. Okay, so for every O that contains A, the outer measure of A is less than the outer measure of O. Okay, so therefore outer measure of A doesn't exceed m double star of A, which is defined as infimum, as the greatest lower bound, and m star in this case it looks like just a lower bound. Okay, so now recall that in class we proved the following result, that for every subset of R and for every epsilon greater than 0, we can find an open set O so that the outer measure of O is less than or equal to outer measure of A plus epsilon. Okay, so therefore that m double star function, which is of course is not greater than the outer measure of O for every open set that contains A, and also it's not exceeding m star of A plus epsilon. Okay, so now we just combine these two inequalities, star and this one, to obtain the following. So we have that outer measure of A doesn't exceed that m double star of a, which doesn't exceed m star of a plus epsilon, and it's true for every epsilon greater than 0. So now if epsilon goes to 0, so for example we can consider epsilon equal 1 over n, we obtain that actually the outer measure of a is this new set function m double star of a.